Hello everyone, welcome to a lecture on digital logic design. In this lecture, I will teach you what are register and how can we design registers. Registers are basically sequential circuits that are used to store n bits of data. Uh, Flip-flops are the main ingredients of this kind of sequential circuits. Registers are very important sequential circuits which are used in digital systems in particular and digital computers to store data. They are very important component for storing n-bit of data. If we need to design an n-bit register, then we need n flip-flops to store n bits of data. To begin with, as flip-flops are the main ingredients of registers, I'll talk about a D flip-flop. D flip-flop is a sequential circuit which stores a single bit of data. Here in the diagram, we can see a D flip-flop, and this D flip-flop has been implemented using NAND gates. We can see we have 5 NAND gates. This is the basic part of the D flip-flop, which has been implemented using 2 NAND gates. And then we have another group of 2 NAND gates here, and then a single NAND gate. And we have a single input that is called D, D for data. And we have a clock pulse, CP, which is connected to the flip-flop through these 2 NAND gates. And we have 2 outputs, one is Q and the other is Q prime, and they are the complement of each other. And when it is in the determinate state, Q and Q prime are the complement of each other. So when one is given, the other can be achieved. The complement can be achieved directly, or it can be achieved from the same output by inverting, by using an inverter. And we assume that the clock pulse is 1. Then changing the value of the input D can change the state of the flip-flop. So the output of flip-flop, which is designated as Q, is the current state of the flip-flop. And if we want to determine the next state of the flip-flop, then we have to change the input D, so we can then determine the next state of the flip-flop. So here we can see that these outputs, Q and Q prime, have been fed back to these 2 gates, gate 1 and gate 2. Let me show you how can we change the state of the flip-flop provided the current state of the flip-flop. So to begin with, here we have the characteristic table of the D flip-flop. We have 2 inputs. We always assume CP, the clock pulse, as 1, so we don't mention that in the characteristic table of the D flip-flop. Q is the current state of the flip-flop, and D is the input. So if Q is the current state and that is 0, and D input is 0, then D flip-flop, in the D flip-flop, when we provide 0, we will get the next state as 0. Let me explain how can we get the next state 0 when the current state is 0 and the D input is 0. So we have 0 here. The current state, which is the output Q, is 0 here. So we have 0 bit here, and we have to remember this. And we provide 0 here. So when 0 is provided here, this 0 will produce a 1 here. And this is the S input. S input is 1. And when this 0 comes here, this becomes 1 here. And when we both of the inputs of the NAND gate 4 are 1, so we get 0 here. So we get 1 and 0 here. Remember that this is the reset input, and this is the set input of this basic flip-flop implemented with NAND gate. So this is set, this is reset. We got 1 here, we got 0 here. So in the basic flip-flop implemented with NAND gate, when R is 0, which is here, and S is 1, it will reset the flip-flop. By resetting, we mean we change the value of the state to 0 if it is not already 0. As it is already 0, we get at 0. Even if it was not 0, you would still get it 0. So when we give 0, we get the next state as 0. Let me explain how can we, when we provide 1 at the input, we get the next state as 1 if the current state is 0. So let me explain. We have Q is 0 here. So when Q is 0 and the D input is 1 here, we provide 1 here. We provide 1 here. So both of the inputs are 1 here. So we get 0 here. So the S input is 0. And when we provide 1 here, we get 0 here. And when one of the input is 0, we get 1 here. So S is 0, R is 1. It will set the flip-flop. By setting, we mean it will change the output Q to 1, which is here. So the next state, which is represented with QT plus 1, the next state becomes 1. When we provide 1 here, we get 1 here. And how we got 1 here, let me explain this part of the flip-flop for this particular case. When we provided 1 here, we got 0 here and we got 1 here. So we had 0 here and we had 1 here. For the NAND gate, when one of the input is 0, we can directly predict that the output is 1. We had 0 here for the S input, so we would get 1 here, and which is already shown here. When this one when we get this one will be given to gate number 2, and we already had 1 from this part of the inputs. So 2 of the inputs are 1, so we get 0 here. So Q prime is 0 and Q is 1. So this state is called set state. So by providing 1 here, we get 1, and when we provided 0, we got 0. The same is the case for the other inputs. Even if the states are 1, the current state is 1. When the current state is 1 and we provide the same input 0 and 1, it will not affect, the current state will not affect the next state, and we will get by providing 0 at the D input, we will get 0 at the next state. And similarly, when we provide 1 here, you will get 1 here. Let me explain this case. How can we get 0? So Q, which is the current state here, it is 1, and 0 is the D input. 0 is here. So what we have now, Q is 1, the current state is 1, and the current input is 0. So let me explain how can we get 0 at the output. When we provide 0 here, even if the current state is 1, we get 0 here. The next we get 0 at the next state. Okay, so we have 0 here, so 0 is given here, so we get 1 here. At the S input, we get 1, and when we provide 0 here, we get 1 here, and both of the inputs are up gate number 4 or 1, we get 0 here. So at reset input, we got 0, and at the set input, we got 1. When we in the flip-flop implemented with NAND gate, when we get 0 at the R input and when we give 1 at the S input, it will reset. 0 at the R and 1 at the S will reset the flip-flop. That means Q will change to 0. But let me further explain this. We have F1 here, we have 0 here. So when this 0 is given here, this is the when one of the input of the NAND gate is 0, we can predict its output, which is 1. So Q prime is 1. Now Q prime is given as a feedback to gate number 1, and we already have the other input of this gate number 1 as 1. So both of the inputs are 1, we get 0 here. So Q is 0, which is here. The same explanation can be given for this case as well. When D input is 1, the next state is 1. So from this characteristic table, it is clear that in the D flip-flop, regardless of the current state, the data input determines the next state. So whatever you give here, that is stored in this flip-flop, and that is available at the Q output of the flip-flop. So when we want to store 0, we get 0. When we want to store 1, we get 1. And the same is true for even if the current state is 1. So regardless of this state, whatever we want to provide, we can store that as the state of the flip-flop. Okay, so this is D flip-flop, and this was the characteristic table of the D flip-flop. And here we can describe the same property using the Boolean equation. This is the characteristic equation, and this is the two variable map. So we have two variable in the input, and we have the one single variable for the output, which is QT plus 1. So this is the equation for next state. We have two ones, so momentum 0, momentum 1, momentum 2, momentum 3. So 0, 1, 2, 3. So this is momentum 1, this is momentum 3. So these are the corresponding squares in the two variable map, and we can make a single group of these two squares. So the equation that we get for the QT plus 1 is D. So that means the next state of this D flip-flop is D. That means whatever you provide at the D input, that becomes the next state of the flip-flop. So which was clear also here. So in this flip-flop, if we want to store 0, we just provide 0. If we want to store 1, we just provide 1, provided the clock pulse at that particular moment is 1. So this is the graphic symbol of the D flip-flop. Q and Q prime are the two outputs, and D is the input, and CP is the clock pulse. So we will take this graphical symbol to design a 4-bit register in coming slides. So D flip-flop with single input and a clock pulse stores a single bit in its original case. Whatever you provide, that is stored on the flip-flop. Okay, so let me use this D flip-flop in designing a 4-bit register. So when we want to design an n-bit register, we can design it using n D flip-flops. So if we are interested to design a 4-bit register, then we can design one by using 4 D flip-flops. So in the screen, we can see we have 4 D flip-flops here. This is flip-flop 1, 2, 3, and 4. And the Q prime output is not shown because it is not required. If it is required, then that can be taken, but for simplicity, it is not shown here. And it can also be taken, the Q prime output can also be taken from Q by inverting the output. Just use an inverter here, and the same output Q prime can be taken from any output of the flip-flop. Okay, so this is the D inputs are the inputs of the register. So we have a 4-bit register, and each register stores single bit, and the D inputs are labeled as input 1, input 2, input 3, and input 4, because these are the input lines that will be connected to the 4-bit bus to store 4-bit data in this 4-bit register. Here we can have the Q outputs, which are designated as A1, A2, A3, and A4. So these are the 4 bits that can be read from this 4-bit register. And whatever is available here at these 4 input lines, that is stored on the register, or that in other words, it can these 4 bits can correspondingly change the current state of the flip-flops when the clock pulse is 1. So the clock pulse, each clock pulse of the flip-flop is connected with this clock pulse, which is a train-up signal from a clock generator. So when the clock pulse is 1, at that particular time, whatever is available here at these input lines, that will be stored in particular flip-flop. For example, when I is 0 and the clock pulse is applied, this 0 will be stored on this flip-flop, and that will be available at the Q output, which is designated externally as A1. Similarly, at the same time, when I2 is, let's suppose it is 1, then we will get 1 here. If it is 1, we will get 1 here. If it is 0, we will get 0 here. So at the same time, the 4-bit data is applied, and for a moment the clock pulse is applied, and the data, whatever the data is available here, that is stored on the flip-flops, the 4 flip-flops. So we can, this is a 4-bit register, and 4-bit data can be stored on these 4 flip-flops. So we have used 4D flip-flops to build a 4-bit register to store 4 bits data. This clock pulse can be controlled through different means, using an additional input called load. We will see some examples of other 4-bit registers in coming slides that will have some additional inputs as well. Okay, so we will design another 4-bit register with some additional inputs using RS latch implemented with NOR gate. But before going into that kind of register, let me introduce RS latch implemented with NOR gate. So in the diagram here, it is an RS latch implemented with the NOR gate. This is the RS basic flip-flop, and then we have a clocked pulse that is connected to these gates through the NAND gate, these two NAND gates, and these two NAND gates plus this clock pulse make this RS latch as a clocked RS latch. So this is a clocked RS latch, and here we have the characteristic table where we have one is the current state of the flip-flop is considered as the input, and we have the two inputs S, which represent set input, and here we have the R input, which is reset input. And with these two inputs S and R and the current state, we can determine the next state of the flip-flop, which is represented as QT plus 1. And we again assume that the clock pulse is 1 when we want to change the current state of the flip-flop by providing inputs. So we have the current state, we have the two inputs, and we can calculate the next state. So when the current state is 0 and we provide 0, 0 at the S and R input, it will maintain the current state. So whatever the current state we have, it will be maintained. Let me explain how it happens. So current state is 0, so we have 0 here, and we provide 0 here, and we provide 0 here. So both of the inputs of these two AND gates are 0, and so regardless of the clock pulse, we will get 0 here, we will get 0 here. So the R input here is 0, the S input here is 0, and remember that we have 0 at the current state of the flip-flop. Now recall the function of a NOR gate. In the NOR gate, when one of the input is 1, one of the inputs is 1, then we get 0 at the output. When both of the inputs are 1, then we get 0 as well. When both of the inputs are 0, then in that single case, we get 1 at the output. So this is the function of NOR gate. So we got 0 here, we got 0 here. So both of the inputs, one of the input of each of these NOR gates is 0. So we cannot determine the output. But here we have the current state is Q, which is 0. So this 0 is fed back here, and this will make both of the inputs 0 of this NOR gate. So we will get 1 here. So the Q prime is 1. Now this Q prime is fed back to the NOR gate, the upper NOR gate. So we got 0 here, we got 1 here. So one of the input is 1, so we get 0 at the Q output. So Q is 0, which is shown here. So the same explanation can be given for all other scenarios. And here we have the current state is 0, and when S is 0 and R is 1, then this will reset the flip-flop if it is already reset or otherwise. The current state is 0. That means the flip-flop is already in the reset state, and we provided 0 at the S input and we provided 1 at the R input. So by providing this combination, S is 0, R is 1, it will reset the flip-flop. In the previous flip-flop, in the implemented with NAND gate, when you provide a 0 here and 1 here, it will set the flip-flop. So by providing 0 at R or S will reset the flip-flop when the other input is 1. But here, when providing 1 at one of the input and keeping the other as 0, will change the state according to the, if 1 is provided at the R, then it will reset. If 1 is provided at the S input, it will set the flip-flop. And also keep remember that the other input must be 0. And the flip-flop implemented with NAND gate, the other input must be 1. So by providing 0 at the S, by providing 1 here, it will reset the flip-flop. So the same explanation as I did for the for this combination can be given for all the other cases as well. I'm not going into that detail because it is quite simple. Just keep these values for the current state and the inputs, and use the property of NOR gate that when one of the input is 1, then it will provide 0. It will give as 0 at the output. When both of the inputs are 0, then it will give 1 in this single case. So the other combination can also be explained this way, but let me broadly or abstractly teach you what kind of inputs will change the outputs. So by providing S, when S is 0 and R is 0, when both of the S and R inputs are 0, it will keep the state. Whatever the current state is, it will keep the state. When S is 0 and R is 1, it will reset. By providing 1 at the R and by keeping S as 0, it will reset the flip-flop. If it is there, if it is already reset, it will be reset. If it is not reset, it will reset it. So it is already reset here, so it will not change the state. It is a reset. By providing 0, 0, it will keep the state. It is already reset, so it is again reset. But now it is reset, but providing 1 at the S and 0 at the R input will set the flip-flop. So by providing 0, 0, it will keep the state. Whatever the current state is, it will keep the state. By providing 0 at the S, 1 at the R, it will reset the flip-flop. It is already reset, we get it reset. When it is reset, but we want to set it, by just provide 1 at the S input, 0 at the R input. So it will set the flip-flop. That means the current state is 0, it will set the flip-flop, which becomes 1. Here we have when regardless of the current state, if both S and R are 1, then the output, the next state will be indeterminate. We are not sure what will be the next state. So this is an invalid input and we should avoid it. We should not provide 1, 1 at the S input and R input at the same time. One of the inputs must be 0. At least one of the input must be 0. Or if both of the inputs are 0, then it's also okay. It will keep the state. So this is an indeterminate state. When the current state is 1 and we provide 0, 0, as I mentioned before, by providing 0, 0 at the S and R input will keep the current state. So whatever the current state is, here the current state is 1, so it will keep the current state. Here the current state is 0, it will keep the current state. So by providing 0, 0 in the SR latch implemented in NOR gate, it will keep the current state. Similarly, here the current state is 1, which is set, but we want to reset it. Because we provided 1 at the R input, we provided 0 at the 0 input, so it will reset the flip-flop. So it is reset. Similarly, the flip-flop is already in set state and we want to make it set, so it will remain at set state. Similarly, the final combination is the current flip-flop is at the set state and we provide 1, 1. So as I mentioned, regardless of the current state, when S and R input both are 1, then the next state is indeterminate. We are not sure about the output of the flip-flop. So we should avoid this combination of the input for the S and R. So to summarize this characteristic table, a clocked ORS latch implemented with NOR gate By providing 0 0 at the R and S input will keep the state. By providing 1 at the R will reset. By providing 1 at the S will set the flip-flop. By providing 1 1 is an invalid state and indeterminate states. We should not provide 1 1 at the both of the inputs. So this is a 3-variable Boolean function. The next state is a 3-variable Boolean function, and these are the 3 variables. So we can get its equation for the next state by a 3-variable K-map. So this is a 3-variable K-map, and the indeterminate state are represented with the don't care condition, which is X, and the empty squares are the squares for the 0 minterms. So we have this group of 4 squares, and we have this group of 2 squares. So we get this equation S plus R prime Q. This is the equation for next state, S plus R prime Q. And we have a condition for the don't care condition, and that is SR must be equal to 0. That means to avoid the indeterminate state, one of the input in S and R must be 0. If both of the inputs are 0, that is also okay. But one of the input, S and R must always be 0. And if this condition holds, if SR is equal to 0, then that will guarantee that either S or R or both are 0. So this will avoid the indeterminate state when we have both in S and R equal to 1. So as we will always get SR is equal to 0, so this will avoid this indeterminate state. So given this condition, we can determine the next state by this Boolean equation. So this is clocked RS latch, and this is the graphical symbol of clocked RS latch. This is the R input S, this is the clock pulse, and the 2 outputs. There is an additional input, clear. This clear input is used to clear the flip-flop. When a digital system is turned on, initially it may be the outputs may be or the current state may be indeterminate. So that indeterminate state is not good. We should avoid it. So to begin with, there is normally a start button that will clear the flip-flop. So in the digital system, these flip-flops will be cleared to a determinate state, which is normally 0. So and from that point onward, the state of the flip-flop can be set. So the clear input will set or clear the flip-flop. Sorry, it will not set, but it will clear the flip-flop, and that means the current state will become 0. So each time when a digital system is being used, it is cleared on the state of the flip-flops are cleared, and then after that any input can change the flip-flop accordingly. So just to avoid this indeterminate state. So we will be using this RS flip-flop with R and S input, Q is the output, Q prime is the output. The 2 outputs are Q and Q prime, and we have a clear input as well. So by providing 0, it will clear the flip-flop. Okay, so now we can design a register with a 4-bit register with parallel load. Here we have some additional inputs, as I mentioned before, and we have RS flip-flop, and again the Q prime output is not shown here. If it is not there as the output pin, then it can be taken from this Q output by inverting the output. So we have 4 flip-flops, SR flip-flops, and we have 4 outputs connected with the Q outputs of the flip-flops labeled as A1, A2, A3, and A4. So these are the 4 bits that are stored in this register and that can be read from here. And these are the 4 inputs, I1, I2, I3, I4, just like the 4-bit register we have already discussed. Here we have the load input. That load input actually controls the clock pulse. We want to, for example, if you want to the state of the flip-flops to be affected and control it, then we can add an additional input called load that control the operation of the flip-flops or the operation of the register. Another method would be to use an AND gate here at the clock pulse and connect this load with with one of the input of the AND gate here, and here we have an AND gate. One of the input is the clock pulse and the other input is the load gate. So in the AND gate, when load is 0, we will always provide 0 at the clock pulse. Because we have an inverter here, so we could have used a NAND gate here and that could have controlled the operation of the clock pulse, but that would add additional delays as well, so that is not good. So instead, this load input is used to control the inputs. So whenever we want to whenever we want these inputs to change the state of the flip-flop, we can control them using this load input. So now assume these load inputs have been connected to the inputs using these AND gates. Now assume there is an additional just a buffer, and this is just an additional buffer to control its load. When this load input is 0, we get 0 here, and this 0 is connected with the AND gate that controls the SNR input of each flip-flop. So when this is 0, we get 0 0 here. For each SR input, we get 0 0 here, because this AND gate will make them 0 regardless of the inputs I1, I2, I3, and I4. So when load is 0, we get 0 0 at the S and R input of each flip-flop. And as I mentioned before, when we get 0 at the S and R inputs, the current state of the flip-flop is maintained. So whatever has already been stored, it will be kept even if you provide the input. So even if you provide the data here, but as long as the load input is 0, and nothing can be stored on the flip-flops, or nothing can be stored on these registers. So load can control the operation of this register. Even if the clock pulse is 0, this is enabled at the negative edge because of this inverter. So when the clock pulse is 0, it will be enabled. Okay, so this load can control when we want to store the data. So when load is 0, nothing can be stored on the flip-flop, or the state of the flip-flop cannot be changed even if you provide data here. So this is the load input, and here we have the inputs. Remember, we have 4-bit register, so we have 4 bit of inputs, I1, I2, I3, and I4, and each of the input is given directly with the S input and its inverted version with the R input. So this style would avoid the invalid or the input that should be avoided, the input where S and R both are 1. So when 0 is provided here, it will be given 0 will be given to S, provided the load input is 1. So whenever we want to change the state of the flip-flops, we will keep the load input as 1, and then we provide the data here. So for each bit, when let's assume for I1, when 0 is this bit I1 is 0, 0 will be given with S input, and this will be inverted, and the inverted version is given at the R input. So when I1 is 0, we get 0 here, we get 1 here. So it will reset the flip-flop, and that means 0 will be stored here. So when we provide 0 here, 0 will be stored here. When we provide 1 here, 1 will be given here at the S input, and this 1 is inverted here. So it will be 0 will be provided at the R input. So 1 at the S, 0 at the R will set the flip-flop. So it will store 1 here. So as we had provided 1 here, we will store 1 here. So just like the D flip-flop, we can store a bit here. And the D flip-flop, just like D flip-flop, we provided 0 here and we stored 0. We provided 1 here, we stored 1 here. And similarly, in the RS flip-flop, with this treatment and with this additional inverter, when we provide 0 here, 0 is stored here. And the same explanation can be given for all other inputs. So when load is 1, and we provide 4 bits of data, the same 4-bit of data is stored on the flip-flop when the clock pulse is 0 here. When the clock pulse is 0, at that particular moment, the 4-bit available here is stored on these 4 flip-flops, provided the load input is 1. So we can control with this load input, as long as the load input is 0, this data cannot change the state of these flip-flops, or cannot change the state of the register. Or in other words, even if you provide data here, but when the load input is 0, this data cannot be written over to this register, 4-bit register. So this load input is very important to control the operation of the clock pulse. Even if the clock pulse is provided, but with the load input, it can be controlled. So assume in digital system, this load input is a kind of write control signal. So this can be taken from the write output pin of the microprocessor. For example, if we are thinking about a microprocessor based system, and we can now see that how can a write signal can control when to write on the register. So when a write operation is required, the microprocessor will send the data through the data bus, and which will be connected with these input lines, and it will send a write signal here at the load input, and at the next clock pulse the data will be written over to this register. And we have so this was the operation of the clock pulse, as we already know, and the clear input is connected to the clear inputs of each SR flip-flop. As I showed before, that we have a clear input in the SR flip-flop as well to clear its state, because initially it is in the flip-flops are in the indeterminate state. So to make them determinate, there is a clear input. So by providing 0, whenever we want to clear the register, we just provide 0 here. So by providing 0 here, we'll clear all the registers, and all the flip-flops, and it means it will clear the register. And from that point onward, when the load is 1, we can write data by providing clock pulse. So whatever is intended to be written over to this flip register, the data is provided here, and the load input is here. The load is 1, so we can write data onto the register. So this is a 4-bit flip-flop 4-bit register implemented with RS flip-flops, and clear input, a clock pulse, and the data input, and a load control. So this load control is very important. Now next, I will in coming lectures I will explain how can we design a similar register with parallel load using a D flip-flop. So